So as good as my notes were yesterday with those big open circles and you could write everything in, it was really nice and clean. These notes are not as easy to write into because of the weird sharp lines. It looks cool, but not perfect. So write small when you have a chance because you're going to need it. A little bit more writing today, but there's a lot of stuff. We are covering everything we did from like mid-August till October on these notes right here. So a lot of different things we're covering. Product rule and quotient rule are the first two things up. You don't need product rule and quotient rule all the time. You need them when you look at a problem. And what do you have in that problem? A bad question. The correct answer to my bad question is two variables. Okay, two variables. A lot of students will see something like this, like 3 over x squared, and they'll be like, ooh, I need product quotient rule for that. No, you don't. There's one x. If there are two x's, then we need quotient rule. Here, there's only one. Okay, let's quickly remember what's going on. You should not need me to remind you of this, but I'm going to anyways. Product rule. That's the first times the derivative of the second plus the second times the derivative of the first. That is product rule. Tell your neighbor, remind them, what is quotient rule? Quotient rule. TJ, what's quotient rule for us? Low, D, high, minus high, D, low, over low, low. Remember, the lows are on the outside. Okay? Everything on the outside is a low. Do those two. See what you can do. Use product rule on the top, quotient rule on the bottom. See what you got. Let's go here. Top one, we're doing product rule. Jordan, talk me through product rule. What'd you get? First, so x squared times the derivative of the second. The derivative of e is what you see, so e to the x. Then what? Plus, in parentheses, wonderful, times the derivative of the first, which is 2x. That is his derivative first times derivative of the second, plus second times derivative of the first. On the bottom, we are doing quotient rule. Kate, talk me through quotient rule down here. Low, D high, and then 2x squared minus 1 times 3x squared. Wonderful. X cubed squared, or x to the sixth. Perfect. That is our quotient rule. Questions with quotient rule? Let's go over to this box. I'm going to draw a line kind of down the middle here and make sure we can handle this. In the top, find the derivative. Okay? There are lots of different ways we can say find the derivative. Brainstorm with your neighbor. What questions could they ask that mean find the derivative? So, Vincent, what's one way to say find the derivative? More specifically, find slope. Slope at a point. If we are finding the derivative, that is a slope at a point. Wonderful. Allie, what else you got for us? Ooh, the fancy one. The limit as h approaches 0 of f of x plus h minus f of x all over h. That is the limit definition of a derivative. Good. Don't forget that that just is a fancy way to say find the derivative. Skylar, what else you got for us? dy over dx. That is another way of saying find the derivative. Parker, what else you got for us? Y prime, wonderful choice. Y prime is another way of saying find the derivative. Chloe, what else? Ooh, the long one, instantaneous. Instantaneous. Rate of change, good. Tyler, what else you got for us? The other limit one, good. The limit as x approaches c of f of x minus f of c all over x minus c. I know you can't really read that, but the other limit one, good. Raiden's group. What else you got? Oh, boo. F prime. Yeah, let's go. F prime. Wonderful. Velocity given what? Given position. Yeah, we could do all those. Given position, find velocity. Good. Given position, find velocity, or find velocity, find acceleration, or given velocity, find acceleration, and so on. I think we did a pretty nice job there. Anyone else I'm missing there? I think we're pretty good. That's pretty good. Anti-derivative? Oh, and so anti-derivatives. Yeah, we're not quite there yet. Good. Down below, don't forget to rewrite. Okay, I'm just making this up and adding my own space here. But don't forget to rewrite derivatives. If it doesn't have two x's, then you don't need product rule or quotient rule. Okay. For example, let's say I gave you 2 over 3 cube root of or square root of x. 2 over 3 square root of x. Do not try to take the derivative like that. Okay? We want to rewrite that. And a couple things we could do. If it's just numbers, pull numbers out in front. So what number can I pull out in front here? 2/3. Pull out constants. So I can just write 2/3 times the rest of this stuff. The x is on bottom, so what am I going to write if x is on bottom? Negative. It's the square root. So instead of square root, I can rewrite those as fractional exponents. What's my fractional exponent going to be? 1/2. Okay? 2/3 x to negative 1/2. You can take that derivative all day long. When it looks like that, all of a sudden your brain starts getting scared. Don't be scared. Rewrite it. We good with that? Rewrite exponents. Or rewrite all that stuff. E and ln. There's no good way to write E and ln, but you could write them in here if you really wanted to. If f of x is equal to e to the x, what is f prime of x going to be equal to? The derivative of e is what you see times the derivative of the exponent. But the derivative of e to the x is e to the x. The derivative of e is what you see times the derivative of the exponent. What about, let's say g of x was natural log of x. What is g prime of x going to be? 1 over. Okay? 1 over the baby times the derivative of the baby. If it's just natural log of x, it's just 1 over x. Don't forget those two basic derivatives. We use them all the time. Find the two down below using those rules. Go. Derivatives here. I'm taking the derivative of y equals 3x squared, or e to the 3x squared. Maya, what do you say that derivative is going to be? E to the 3x squared. So the derivative of e is what you see times the derivative of the exponent. Good, 6x. We are then taking the derivative of natural log of 2x minus 3. Lauren, what's that derivative going to look like? Times 2. 1 over the baby times the derivative of the baby, which would be times 2. Good. Next one here is chain rule. When we talk about chain rule, what big thing is going to show you, oh yeah, you need to do chain rule here? What would be true about the problem? Parentheses. Don't forget about parentheses. If you see parentheses, there's a good chance you need it. Not always, but if there's something important inside of parentheses, like there's an x inside of parentheses, there's a pretty good chance you need chain rule. Okay? Chain rule, remember that's the mama and the baby. You take the derivative of the mama, you rewrite the baby, and then you take the derivative of the baby. This problem right here, y equals sine to the 5th power of x squared minus 1. Remember, we don't really like it written like that. What could I do with that 5? Remember, that's the same thing. Putting it like that, putting the 5 on the outside. So if you were to do this problem right here, what would you need to use in order to solve that guy? Okay, work on that problem, see what you can do. Okay, now do it. Anybody want to take a shot at this one? Angela, what you got for us? What's going to go on the outside of this? 4. So she wrote the 5 in front. She subtracted 1 from her exponent. What's going to go inside the parentheses? Good. She rewrote the baby, so sine of x squared minus 1. Then what'd you do? Cosine. She took the derivative of this inside here, so she wrote cosine. And she rewrote that baby, x squared minus 1, times the derivative of that baby, which is 2x. A big old ugly problem. We could simplify it, but we're not going to. We're going to leave it like that. Questions on chain rule? Down below, let's talk about motion. So if we're talking about motion, a lot of these things you already know, but let's just make sure we're aware of them. S of t, okay, or sometimes they might use x of t. They go back and forth, but that means what for a problem? That's position. And if I take position and I take the derivative of it, what's the derivative of position going to tell me? V of t. V of t is velocity. That's the derivative of position. And if I take the derivative of velocity, that's going to tell me A of t, or acceleration. Okay, it's things you already know, but I'm just going to write them down anyways. The one thing in motion that I think we probably spent the least amount of time doing, and you might need an actual refresher on, is speed. When we talk about speed, what is our definition of speed? The absolute value of velocity. So if the speed of something is 4, what does that tell you about the velocity? What was the velocity if the speed was 4? It could have been 4 or it could have been -4. We really don't know. Either one is fine because we're talking about the absolute value. Something that maybe you put a star by because we might have forgotten what speed means. Okay, so don't forget about that. Let's act like we were talking about speeding up versus slowing down. If something is speeding up, what's going to be true about that problem if it is speeding up? V of t and A of t, we're looking at those two things, are what? Same sign. V of t and A of t are same sign. If you're slowing down, V of t and A of t, different signs. Speeding up versus slowing down. We do that all the time, but just make sure we know it. Last thing about velocity or motion in general. Let's say I told you a particle was moving left or down. What would be true about that particle if it's moving left or down? Velocity is less than 0. Velocity is negative. If your velocity is negative, you're moving left or down. Differentiable. If I'm telling you something is differentiable, what is true about it if it is differentiable? It has to be continuous. It's got to be continuous if you're differentiable. What is an example of a graph that is not differentiable? Or what would be true about a graph if it were not differentiable? Cusp. Or cusp is a fancy word for corner. So cusp or corner is bad. What else would make you not be able to find the derivative of it? Asymptotes and holes. I agree with that. That's because it's not continuous. But let's say it was continuous. Cusps and corners would be bad. Something else happens a lot. That would also be discontinuous. So jump. A vertical tangent would be another one. So if that line went straight vertical, that slope is undefined, so we cannot take the derivative of that. Technically, there was another one. It's when your graph jumps back and forth like this, where it's like oscillating completely back and forth. I'm not going to really write that down. I've seen that one time ever on a test, and it was on a graph, and it was pretty obvious that it was not there. Let's look at this one. So probably the hardest part of this paper is this equation right here. The directions would be something like find C and D so that F is differentiable. So we want this piecewise function to be differentiable. So you need to figure out what could C and D be to make that thing differentiable. If something is differentiable, it needs to be continuous and differentiable. Talk with your neighbor for a second. See if you can think your way through that before I show you. Here. If I want to be differentiable, two things need to be true. I need to be continuous, and I also need to be differentiable. This top thing is a line. This bottom one is a parabola. Is a line continuous? Is a parabola continuous? Yeah, I know those are continuous. There's only one place that could maybe not be continuous. What do I need to do with those two equations to make sure that they are continuous all of the time? Set them equal to each other. I'm going to take cx plus d and set that equal to x squared minus cx. What is the only x value that I really care about? 2. Okay, so this is when I'm really finding the limit as x approaches 2 from the left and from the right. I'm going to plug in 2. Okay, and so I'm going to get 2c plus d equals 4 minus 2c. I plugged in 2 for x because it's the only place where maybe they're not continuous, because lines and parabolas are both continuous by themselves. If I were to solve this thing, I could add this 2c over, and I could get 4c plus d equals 4, which is great, but I have two variables, and if I have two variables, I can't solve it. So I can't solve this equation. I need another equation in order to figure out what c and d are. So that's when it's going to be continuous. I also need them to be differentiable. So how can I make sure that these two things are differentiable? A line is differentiable. A parabola is differentiable. Where's the one place I need them to be differentiable? At 2. So now what I'm going to do is I'm going to take these same two equations, but I'm going to set the derivatives equal to each other, because I want their slopes to be equal at 2. So this is where it gets a little tricky. I'm taking the derivative of cx plus d. Remember that c and d are just representing a number, a single number. They're constants. What is the derivative of cx plus d going to be? It is just going to be c. Imagine I asked you to take the derivative of 2x plus 4. Okay? If I gave you 2x plus 4, the derivative would be 2. So the derivative of cx plus d would be just c, that number in front of the x part. So there's my first one. The second one, I'm taking the derivative of x squared. Oh, that's going to be 2x. And the derivative of minus cx would be minus c, because the derivative of negative 3x would be negative 3. There's my derivative. What do you think I'm going to do with that derivative? Solve for c. What's going to go in for x here? 2, because I'm figuring it out when x is 2. So c is going to be equal to 4 minus c. I'm going to add c over. So my c is 2. That is what my c value needs to be. If I know what my c is, what else do I need to do? Substitute. 8 plus d equals 4. D equals negative 4. Those are the two things that you need here in order to solve, in order for that to be differentiable. Questions on how to decide if something is differentiable? Limits need to be equal. The derivatives need to be equal. 2 more, and these ones are pretty easy. Trig derivatives. What things are we thinking about with sine and cosine? What is the phrase we remember to remember the derivatives, sine and cosine? Snapchat. Negative Snapchat. Boom. Boom. Circle of trig. We're going to go around and around in a circle. Okay, we know that here, as soon as we get back from break, we're going to start going the opposite way. Right now, we only go clockwise, but eventually we're going to go counterclockwise as well. That's our derivative. Okay, you need to know your basic trig. I'm not going to go through them right this second, but you need to know pi over 3, pi over 4, pi over 6, and the 4 major axes specifically. If you don't know those, you don't know any trig. Okay, but you need to know those specifically. And then you also need to know if f of x is equal to tangent, what would f prime be? And if g of x was equal to secant x, what would g prime be? Talk with your neighbor real quick. Come up with those two. What is the derivative of tangent? Secant squared x. The derivative of tangent is secant squared. That is something you need to remember. What is the derivative of secant? Secant x tangent x. That is the derivative of secant tangent. It's been a long time since we've done them. They are not as important as sine and cosine, but they're absolutely going to be on your AP exam. Okay, they can absolutely be on your final. Make sure you got those down. Last category is the easiest one. Average rate of change. What does average rate of change mean? Slope. More specifically, what kind of slope? A 2-point slope. We just had this on our last test and we forgot it, but it is 2-point slope, like y sub 2 minus y sub 1 over x sub 2 minus x sub 1. That is what average rate of change means. Okay, you find the slope between 2 points.